Hey guys, today we're going to talk about continuity. Um, for a function to be continuous, that function has to have no gaps, no holes, no jumps, meaning think about those piecewise functions where we have like one piece goes here and then the other one jumps up and does something like that. And also no vertical asymptotes. Horizontal asymptotes would be okay because that doesn't cause a function to not exist somewhere. So again, we're just thinking about places where the graph might not be connected or defined. A hole in the graph. Jumps we talked about, vertical asymptotes, something like this. Okay. So what's our official definition of continuity? You're going to see this pop up, especially in multiple choice problems, but possibly somewhere as a piece of a free response. So continuity at a point is defined as follows. A function f is continuous at c if the following three conditions are met. So first of all, f of c has to exist. F of c exists. That would mean that there's no hole in the graph or no vertical asymptote. Also, the limit as x approaches c of f of x has to exist as well. And then finally, the third piece, these two values have to match each other. The function value has to be the same as the limit value. So f of c has to equal the limit as x approaches c of f of x. And so if they don't match, you just don't have a continuous function. Continuity on an open interval. So a function is continuous on an open interval, a to b. So we can sketch that. Like let's just say, give yourself a little x and y axis. Let's mark off an a here, b here. An open interval just means our endpoints on this interval might be open circles. F of a and f of b are not defined. But give yourself some sort of continuous function, no gaps, holes, or jumps in between there. This is a continuous function on the open interval for all points between a and b. So that function is called everywhere continuous since our limit value matches our function value anywhere between there. There are two types of discontinuities, removable and non-removable. A removable discontinuity would be holes in the graph. We say those are removable because think back to your graphing rational functions days. We could factor the rational function, cancel out a factor in the denominator, and so that if something canceled, all of a sudden it was no longer a vertical asymptote, it became a hole in the graph. So we can kind of remove that by simplifying the function. And then non-removable, those are vertical asymptotes. Because even if you simplify a rational function, whatever was left in the denominator, that was the vertical asymptote, so non-removable. A discontinuity at C is called removable if it can be made continuous by appropriately redefining f of c. So again, all that means is like I can redefine f of x by just simplifying something. So let's just say this is my function. I don't know. Maybe f of x is x plus 1 times x minus 1 over x minus 1 squared. Oh, that's a poor example. Sorry. Boop. Let's say like times x plus 3. I can cancel these out and redefine the function. So this blue function, my simplified function, I could say, oh, that's a new function, and it is continuous at x equals 1. But I have to be careful when I'm graphing this thing. There'd still be a hole at 1. So if that just confused you, I'm just trying to explain what some of this definition is, but it's really, for what we're doing, we don't really have to get too wrapped up in that. So determine whether or not the function is continuous at each of these given points, a through e, and if it's not, we need to say which condition was broken. Going back here, is it condition 1, 2, or 3 that's causing us a problem? Okay, so we have a discontinuity A. It looks like this is a vertical asymptote. So is it continuous? No. What's the problem here? Well, there are several problems. f of c doesn't exist. I'm going to write equals no solution. Also, the limit doesn't exist at a because this goes to infinity. It's not a concrete y value. So also the limit as x approaches c of f of x. Let's just write d and e underneath that. Oops, I said c. Sorry. The limit as x approaches a and f of a. My mistake. If we look over at b, does f of b exist? Yes. F of b is defined to be this point. But is it continuous here? No, we have a jump in the graph. So even though the first condition is met, the second condition has failed. The limit as x approaches b of f of x does not exist. And that's because the left-sided limit does not match the right-sided limit. For part C, is this continuous at C? Well, we have a hole in the graph. Even though f of C is defined, that's not continuous. We're breaking rule number 3. So again, no, not continuous. Why not? Well, f of c exists. So definition 1 is met. The limit exists. It's this value here, whatever this comes out to. But the third issue, f of c is not equal to the limit as x approaches c of f of x. At d, we're almost there, not continuous only because that function value is not defined. So if that were filled in, we'd be good to go. So no, not continuous because f of d is not defined. And finally, we get to the last one where yes, this is continuous because f of e exists. The limit as x approaches e exists, and it happens to be the same value as whatever f of e is. Basically, we're all zeroing in on the same point. Definition of continuity on a closed interval. So a closed interval just means now let's go ahead and include these endpoints. So let's sketch a little graph here. I'm going to do pretty much the same thing. Mark off an A and a B. The endpoints are going to be closed. And I'm going to just sketch a continuous function in there. So a function is continuous on the closed interval if it is continuous on the open interval. So it's continuous in the middle is all that's saying. And we have to make sure that just like this picture, see how the limit of the graph to the right of A is the same as the function value at A? And the limit as I approach on the left of B, that matches whatever f of B is. So we have to make sure that we write that down officially. But that's what's happening. Basically, your graph needs to meet up at the endpoints. There can't be any skips or jumps or gaps there. So how do I say that? F of A is equal to the limit as x approaches A from the right, because you're on the function on the right side coming at A, of f of x. And f of b would have to equal the limit as x approaches b from the left side, because again, the function is to the left of that endpoint b of f of x. So as long as that's true, then we are continuous on the entire closed interval. So again, just keeping in mind your 3 requirements to have a continuous function. Find the x coordinates only, if any, at which f is not continuous. Our first function is polynomial. Think about polynomial graphs. There are no points at which they're undefined, so this is continuous everywhere. Oh gosh, can't spell, guys. Continuous everywhere. We're supposed to be saying x coordinates where it's not continuous, so I wouldn't write like all real numbers or something because that's not what that's asking. I have a rational function for number 2, so first let's factor, see what we're working with here. Okay, so the x plus 2's cancel. This function simplifies to 1 over x minus 5. So be careful here. There are 2 discontinuities. There's a discontinuity at x equals 5. Let's make a note here. That is non-removable. And if you need to tell yourself, that's because it's a vertical asymptote. So if you need to make that note, that would be a good idea. There is also a removable discontinuity at x equals -2. So remember, if you were graphing this back in your math 3 days, you'd have to plot a hole at -2, -1/7, I guess it would be. So there are two discontinuities. If you want to make a note to yourself, that's from the hole in the graph. Let's see, think about the secant x graph. We graphed those in pre-calc last year, okay? Well, secant is the reciprocal of cosine, so anywhere cosine is equal to 0, secant will be undefined. So that's what we need to think about. When is cosine equal to 0? When the x-coordinate is 0, which is at the top and the bottom of the unit circle. Pi over 2, 3 pi over 2, go around again. So let's think. Pi over 2. To get to 3 at pi over 2, you would add pi to that. And you could do that any n number of times. And remember the little notation you have to write there? N is an element of the integer number system. We liked to say NES in my class last year because that was a lot easier. Don't forget NES. So anytime you're describing a series of asymptotes like that, put this little NES statement here. All right, what about D? X plus cosine of x. Well, the cosine graph has no vertical asymptote, so it's defined across all x values. And what if I add x to that? So x has to be a real number, right? So think about values for x. It's like pi over 2, pi over 4, 0, 10 pi, whatever. No value for x is going to cause this to be undefined, so this is continuous everywhere. Let's start abbreviating here. We've seen graphs like part E before. I know this is not continuous at 5. Remember, that's where the breaking point is. You have this graph that kind of looks like, oh, that's a bad sketch. A graph that looks like this. It's either 1 to the right of 5 or it's -1 to the left of 5. So where's the discontinuity? It's at x equals 5. And can I somehow remove that? No. So that's non-removable. I know I wrote vertical asymptotes before, but a jump is also something that you can't remove. I can't just simplify the function the way that it is because of the absolute value. All right, for the next one, when we factor this into x plus 2, x minus 2, it's going to allow us to simplify the function. It'll just be f of x equals x minus 2. Now, even though the x plus 2 is canceled, there is still a discontinuity at x equals -2. It's removable because it's a hole. Remember, this graph will look linear and it'll have a hole at -2. All right, let's pretend these are multiple choice questions so that we don't have to formally write out our work for this. So what would I be doing here? If I want to check if this is continuous, I need these two pieces to meet up at the same point. So all I'm going to do is make a note to myself. If I plug 3 into this one, what number do I get? 3 divided by 3 is 1, plus 1 is 2. If I plug 3 into this one, 3 minus 1 is 2. Since these two pieces match and f of 3 is defined, if you're plugging in 3, you get it here. Since they're both 2, there are no discontinuities. This is continuous everywhere. If you want to show yourself the work and do the official limit notation, fine. You could also graph this thing if you want to verify. But again, all of those things take time, and time is not a luxury on the AP test or for our in-class tests and quizzes. Let's do the same thing for H. Plug in 2. 2 times 2 minus 1 is 3. 2 divided by 2 is 1. The right-handed limit and the left-handed limit do not match. So this is not continuous at x equals 2. That's the breaking point of this graph. X equals 2, that would be non-removable because there's nothing you can do to redefine this function. There's no way to simplify it. All right. For this one, when it's x is not equal to 4, this will give me the limit value. So if I plug 4 into this, I get 16 minus 8 is 8. The function value at 4 is only 7. Since those don't match, there's a discontinuity at x equals 4. And again, it's non-removable. All right, for part J, I see a rational function inside this piece, so I want to simplify that first. So this is x plus 2, x minus 1. So the minus 1s are going to cancel. That's going to help me when I go to take the limit value. So when I plug in 1 using direct substitution, I should get a limit value of 3, even though I originally that would be a hole. If you're plugging in 1, 1, 3 would be a hole there. But then this says for h of x, when x equals 1, just make the function value 3. So that makes it continuous. This would have been a linear graph with a hole at 1, 3. But then the second piece says, go ahead and fill that in. Continuous. So continuous everywhere. Okay, the limit as x approaches 0, sine x over x. Remember, that's one of the ones we talked about on Friday that you need to have memorized. This is only true that this limit value is 1 if x is approaching 0. So if this would have said x approaching 1 or 2 or 3, whatever, we'd have to plug that in and see. But otherwise, this is equal to 1. And fi of 0 equals 1. So this is continuous everywhere. Okay, this is common for a free response. So find the value of a so that f of x is continuous for all x. If you're doing this for a free response question, make sure that you're not skipping steps. You need to use your definition for continuity to justify what you're doing. So if I want f of x to be continuous, that means that f of 1 has to equal the limit as x approaches 1 of f of x. So I need to have this statement here before I just start plugging in numbers and going crazy. All right, f of 1, you're supposed to plug that into the top piece. 1 plus 1 is 2. The limit as x approaches 1, well, I need to plug it. It's got two sides, so I need to plug in that limit and see what's going on there. So I might do that off to the side. Let's see. The limit as x approaches 1 from the, where am I? Oh, duh. What am I saying? I don't need to plug it into two pieces because I just used the top piece to find the function value, okay? So it wouldn't make any sense to plug that in there. I need to just plug into the bottom piece, plugging in 1 for x. So 3 plus a times 1 squared is 3 plus a. And then I can just solve for a. A equals -1. The question just said find the value of a. It didn't ask you to go back and actually find the limit value or anything like that. So you're finished at that point. Okay, number 4. Which of the following are true? So let's see. 1. The limit as x approaches 1 of f of x exists. Is that true? Well, remember, if you see a rational function in here, you need to simplify it before you decide if something's true or not. So the x minus 1s cancel out. You are able to use direct substitution into the simplified function. 1 plus 1 is 2, so yes, 1 is true. F of 1 exists. F of 1 is defined right here as 4. So yep, that's true. F is continuous at 1. Well, the limit value 2 did not match the function value 4. So 3 is not true. So I'm looking for 1 and 2 only, which would be C. Given this function, without a calculator, draw the graph. So again, you did this so much in both Math 3 and pre-calc that I shouldn't have to explain how to graph these, but if you need a refresher, that's what office hours are for. I'm factoring, I'm canceling, seeing what I have to work with. When I draw this graph, there's a vertical asymptote at 4. There's a hole at -1. Remember, you plug in to the simplified function so you don't get 0 over 0. So -1, -1/5. So let's get some of this down. So at 1, 2, 3, 4, vertical asymptote, hole at -1, -1/5, put that there. What else? If I plug in 0 for x, If I plug in 0 for x, I get negative 1/4 for y. So there's like a y-intercept. There's a horizontal asymptote at 0 because it's bottom heavy. Oops, my points, sorry. Oh, goodness. My points for 1/4 and 1/5, I had those backwards. 1/5 is closer to the x-axis than 1/4 is. My bad. My scale's a little off here. There are no x-intercepts, but we should know that a rational graph has branches that look like this. If I were to plug in something like 5, I would get 1/1. So there's a nice point. Okay, so without a calculator, yes, I can give myself a sketch of that graph. And it's important to sketch it well, like having these vertical asymptotes and holes defined, because it says name the values of x for which f of x is not continuous and state removable or non-removable. It's easy to forget that there's a hole in the graph if you're just going off of like a sloppy sketch. So at x equals 4, there's a non-removable discontinuity because you have a vertical asymptote, and at x equals -1, there's a removable discontinuity, and that is because that's a hole. Number 6, redefine the function f of x equals that when x equals 3 so that the function is continuous for all real numbers. So what does it mean just redefine the function? Redefine the function means work on this thing, simplify it, manipulate it somehow so that you actually could direct substitute 3 in. Because if I try direct substitution right now, for 3, I get square root of 4 minus 2 is 0 over 3 minus 3 is 0. So what do we mean by redefine the function? It's just, let's work on this thing and try to get it so that direct substitution works. We did this on Friday. Let's multiply. When I see a radical in a numerator, let's multiply by the conjugate, which would be square root of x plus 1 plus 2. Do that in the top and the bottom, which is legal. You're just multiplying by 1, a very fancy 1 right here. And remember, the rule for this is to go ahead and distribute through the numerator, but don't distribute through the denominator. So multiply the first terms together to get x plus 1. The outside and inside two radical x plus 1s will cancel. 2 times 2 is minus 4. Over, leave it like this, x minus 3. I don't want to distribute because the way that these problems should always work out is that the numerator, which simplifies to x minus 3, will cancel with that extra piece in the denominator. So you have 1 over square root of x plus 1 plus 2. This is the redefined function. So maybe I'll call it like g of x. Okay, so g of x could equal 1 over square root of x plus 1 plus 2. This graph should have all of the same points as the f of x graph. Like if you were to put those in y1 and y2 and investigate, f of x would be undefined at 3, but g of x would be defined at 3. You can plug in 3 and get 1 over square root of 4 plus 2, so 1/4 would be g of x. And that would be the only difference between those two functions. So that's what we mean when we say redefine the function. Number 7, f of x is this piecewise function. Is f of 4 defined? Yes. F of 4 equals 20. Does the limit as x approaches 4 of f of x exist? You'd be in the top part doing direct substitution. 20 minus 2, yes. That limit is equal to 20 minus 2, 18. Is f continuous at 4? No, because the function value is not equal to the limit value. Number 8, g of x is this piecewise function. Find the value of b so that the function is everywhere continuous. Start with your limit, or start with your definition of continuity. That means that g of b, I'm sorry, not g of b, gosh. Where does this split off? G of -1 needs to equal the limit as x approaches 1, -1 of g of x. Can we find g of -1? Yes, we can plug it into the bottom function, and that would give me -1 minus b. Can we find the limit as x approaches 1? Now, you can't plug it into the bottom because you're going to get -1 minus b, and everything will cancel. You need to plug it into the piece you haven't used. Because again, if this is continuous, the left and the right-sided limits should come out to the same value. So if I plug in -1 for that, I get -3 plus b. Okay, solve for b. I'm going to add b to the right side to b. I'm going to add 3 to the left side. That would equal 2. And b would equal 1. Find the value of b is all it asked for, so that's my final answer. And finally, last example, redefine the function h at 5 so that the function is continuous everywhere. So again, all this is saying is let's come up with some other function that we can have all the same points as h of x, and it'll just be defined at 5. So this is factored x minus 5 times x plus 4 over x minus 5. So my other function, my redefined function, would be like, oh, let's say g of x is just x plus 4. G of x shares all the same points as h of x, except h of x is not defined at 5, and g of x is. G of 5 would equal 9. And again, if you're confused about what that means, just put h of x, the original, into y1 and put g of x into y2, and you're going to see that they graph on top of each other. And if you find the value at 5 for each function, one will be blank and one will show you 9. All right. We need to switch over to intermediate value theorem. Let me check. Am I doing this on the same day? Sorry, guys. Yeah. Okay, we're doing this on the same day. So intermediate value theorem is like an existence theorem. We can shorten it to IVT. There are only a couple of theorems this year that you have to cite, so this is one of them. If f is continuous on the closed interval a to b, and k is some number between f of a and f of b, so k is a y value, and it's between the end y value on each segment that you're looking at, then there's at least one number c in a and b such that f of c equals k. So it's hard to read that and sort it out. Just look at these pictures. Here's a continuous graph on this interval between a and b. Here's some c value where the value of k, that y value, falls between f of a and f of b. That's all that's saying. Here's another example. This is a continuous function between a and b. There are 3 c values for which we hit this one k, and that k falls between f of a and f of b. Here is a function that is not continuous on the interval a and b, and so there is no c value for this particular k. All right, so the rule for IVT, intermediate value theorem, is that we have to have a continuous function between a and b to be able to say with absolute certainty that there'd be at least one c value, that we hit this y value, this k. All right, so examples. A person's height. So we assume height is a continuous function. If a girl is 5 feet tall on her 14th birthday and then 5'6" on her 17th birthday, then for any height between 5 feet and 5'6", there must have been a time at which her height was h. So as long as h is somewhere between that 5-foot mark and that 5'6" mark, at some age she hit that h, whatever it is, whether it's 5'2", 5'3", 5'4". Oh, sorry, my work's already in here. Oh, and I can't erase it. That's not good. All right. Hold on, guys. Sorry. Fast forward through all this for me. Let me find my document I can actually edit. Okay, here we go. We're not going to do the mixed review together. We're going to just do this piece. Okay, so intermediate value theorem can be used to verify zeros. It cannot be used to find them. It's just, do zeros exist? So existence theorem. All right, so what do we need to do to figure this out? So first we need to check, is the function continuous on this interval? So is f of x continuous? Well, f of x is polynomial, so f of x is continuous on 0 to 1 on that interval, so check. Okay, then we need to make sure that the endpoints, that we know what those values are. So what is f of 0? If I plug in 0, I get -2. What is f of 1? 1 plus 3 is 4. 4 minus 2 is +2. So how can this tell me that zeros must exist? Well, you can think of this graph. You wouldn't have to graph this on an AP test, but here's what we're saying. Here's the endpoint, 0, -2, 1, 2. This function does something in between. And so at some point, at least once, we cross the 0. Maybe it crosses several times. I don't know. The theorem doesn't tell us that. We could figure it out. But this just says, hey, since there must be, okay, sorry, by IVT, there must be some C, let's say, that falls between 0 and 1, so 0 less than C less than 1, such that, you can abbreviate ST, um, such that f of C equals 0. And that's because we change signs here. F of 0 goes from -2, f of 1 goes up to 2. Since 0 falls in between there somewhere, there must be some C where that exists. Does it tell us what the C value is? No, we would have to factor or investigate graphically or just figure it out. IVT can be used to verify values. If yours said find, this originally said find, it should be verify again. It's just an existence theorem, so it doesn't help us find anything. It just says, hey, yeah, there's something where that exists. So for this one, we're on the interval -3 to 3. It says f of c equals 16. So this is we just want to verify, like, are there some c values that this function hits 16 at? First, we check continuity. Is x squared minus 2x plus 8 continuous on this interval? Yes, it's continuous everywhere. So we need to make that statement to use IVT. And then next we find the endpoints. What's f of -3? That's 9 plus 6 plus 8. So let's see, 15 plus 8, 23. And then find f of +3. That's 9 minus 6 plus 8. 3 plus 8 is 11. 16 does fall between 23 and 11. So by IVT, there exists some C between, this time we're between -3 and +3. There must be some C that falls in here, at least one, such that f of C equals 16. Do I know how many C's there are? No, I would have to set the equation equal to 16 and find it. But again, this is just verifying that this exists. If it said find f of C, then all IVT does for you is verify that it exists. You'd have to solve it separately. So try the mixed review for homework tonight, and then I believe we are on homework number 4. So mixed review I'll be checking the next day in class, and homework number 4 in the textbook is up to you to check your key and ask me questions.